We get to talk about statistical graphs today, and they're so useful to help us visualize data. Not only that, it helps us understand properties in our data, like the mean, the median, the standard deviation. It helps us find patterns, clustering, correlation. The other thing I love when I do graphical data analysis is that it really helps me verify my assumptions, kind of fortify what I've done. Now, we're going to define and identify some basic summaries of data, and we'll look at them numerically and also graphically. And we'll get to do this all in R. So hold on tight. I'm excited to share the IRIS dataset because it's so often used in statistics. And we use it to solve problems in multivariate statistics, even in machine learning. It's a small dataset, but it's so powerful because of how the data was collected. Very high quality, very little error. Now, the data we're using today has actually been celebrated by a British statistician, Ronald Fisher, who in 1936 was actually knighted to become Sir Ronald. Now, the reason I wanted to show you the IRIS dataset is because it's almost like a hazing tradition that we have to hand down in statistics. You have to have used the IRIS dataset. I remember once I was actually analyzing a data set on the airplane, and it was IRIS. And the person sitting next to me looked over and was like, "Are you looking at the IRIS data set?" I was like, "Why, yes, I am." So it's one that so many people have seen before, and I want to make sure that you get a chance to see it as well. Now, one of the reasons that the IRIS data set is commonly used is because if you wanted to, say, compare a new method with an old statistical method, how would you test your new method? How would you maybe show people that what you've come up with is better than what's currently being used? Well, the way that we do that is by testing it on a data set that everybody knows so that we can really compare your method to what's been done in the past. Now, the IRIS data set in particular is commonly used for pattern recognition. This data set has 3 types of classes that each have 50 examples. And each of the classes tells us a different type of iris plant, which is a species. We've got data measurements on both length and the width for each type of flower. And here's the data that we have: the sepal length and width, the petal length and width, and the different classes: Iris setosa, Iris versicolor, and Iris virginica. You didn't know you were going to get a botany lesson today, did you? All right, let's load the data into R. And if you want, you can follow along with me. We're going to load the library data sets because the IRIS package actually lives in that data set. And we're also going to load our color brewer. This helps us add funky colors to our graphs. Now, why is this data set super fun? One of the reasons is that the species is so similar that it's actually difficult to separate visually. An American botanist, Edgar Anderson, he gathered the data and he wanted to look for statistical differences to try to classify each species. So as we generate plots, I want you to think about, are there ways that we might think we can use a certain variable to help classify the 3 species? All right, let's start our analysis. We're going to start out with bar plots. And as you've seen before, we use bar plots to show comparisons across several groups. Now, it might remind you of a histogram, but it's not, because it's plotted over a category. In this case, our category is iris type. Now, one difference you're going to notice right away is that the bars of a bar plot, they kind of have a little bit of space in between them, whereas we don't see that on the histogram when it's plotted next to each other. And now a difference between the bar plot and, say, the histogram is with histogram, we can talk about skewness, right? We can talk about where the data values fall, if it's to the left or to the right, above or below a certain value. Bar plots, however, our x-axis is actually categorical. So it's categories. It's not quantitative. So we can't quite view it in the same way as a histogram, but it still gives us great information. All right, let's generate a bar plot in R of our iris data. And first, I want you to look at the petal length. So the command to do that is bar plot iris $petal.length, and we'll add a title of petal length. All right, check out this bar plot. Notice we've got what looks like some distinct groupings. Your x-axis has petal length, but is by the iris species. So setosa, versicolor, and virginica are all there. Notice how the first 50 of those appear to be sort of down-weighted, have lower values of petal length. And then the second group also appears to have its own middle value. And the top group has a slightly higher value, the last 50 values in that bar plot. You're probably beginning to see, even with this first graph, that there are some distinctions in the petal lengths of the three different species. What about sepal length? Let's see if we can see that same type of distinction when we look at this bar plot. Here's our code to do that. Bar plot, iris, $sepal.length, with the title, main equal to sepal length. That's so we can keep up with them. Whoa, okay, here, same thing. We've got the iris types on the x-axis, but can you really see a distinction between those sepal lengths? It's hard for me to find one. It looks like maybe there's a slight increase, but definitely not quite enough to determine the difference between the species. Now, what if we wanted to do a stacked bar plot, and maybe by color? We want to kind of pull some more information out, and a bar plot lets us do that. Here we've taken that same bar plot of sepal length, but now we've colored it by species, because I wanted to see where are those species overlaying each other in the bar plot. Notice here for the red setosa, it tends to be clustered toward the lower values, between 4.3 and around 5.3. And then we see versicolor picks up in the blue values in the middle, and our largest values tend to be virginica. So even just by coloring this bar plot, you see how we're able to pull more information out of it. Now, summary statistics are our old friend. They're sort of the quick and dirty way that we get information out of our data super easy in R. And often we look at those through a box plot. But first, I want to kind of walk you through a couple of these summary statistics because I want to highlight a couple of things for you. Look here for sepal length and sepal width. You see the minimum value, the first quartile, the median, the mean, the third quartile, and the max. So immediately just looking at your minimum and max, you can see, say for sepal width, from 2 to 4.4, kind of the range of your data and how spread it is. Notice that sepal length, on the other hand, has a minimum of 4.3 and a maximum of 7.9. What about for petal length and width? Well, here, notice petal width, minimum value of 0.1. So petal widths tend to be a lot smaller, and you see that here in the range of your summary statistics. Whereas the petal length goes up to 6.9 at the maximum with a minimum of 1. Lastly, your summary statistics are going to tell you how many groups are actually in each of your species. So we have 50 values for setosa, 50 for versicolor, and 50 for virginica. Box plots. This is going to take your summary statistics and ramp them up, put them on a graph so you can see it all at one time. We use this to compare lots of information about variables. But here, I want to kind of look at them all together. Now, box plots are going to show us those 5 statistically important numbers, the minimum, the 25th percentile, the median, 75th percentile, and the maximum, but it shows us all in one plot. Here's the command to do that in R. Let's do box plot of our iris sepal.length and put a title on it. Nothing too amazing sort of jumps out at me with this sepal length box plot. Notice you see the range of our data from around 4.5 to just over 7.5. The median is highlighted there. What if we wanted to look at all 4 of these next to each other? Now that's going to give us more information because now we can actually compare them and look for possible ways to group them. Here you see box plots for sepal length and width and petal length and width. Anything jump out at you yet? Well, when I look at this, I notice, okay, my sepal length have the highest values, and petal width tends to have the lowest values. Petal length, look at the spread there. Notice sort of the interquartile range for that is the largest among the 4. In fact, the interquartile range of petal length sort of encompasses the sepal width values. And look at sepal width, super tight with some outliers in there, but that's probably the smallest distributed variable. Now, a box plot can also be used to show how one attribute, say petal length, varies with another attribute, like iris type. Here's the command we can use to do that in R. Box plot of petal length, tilde, which tells us we want it to vary according to species. And I want to title this petal length versus species. Now check out this box plot. Notice now we've actually done petal length, but we've done it by species. So we want to see, how does a petal length change among Setosa, versicolor, and virginica? Now you can start to see a separation. Look at Setosa. Notice how it's all clustered, whereas versicolor and virginica, they have a little bit of overlap, but there's still some separation. This clues you in that, hey, this variable might be one that we're going to use to do some separation. Now with box plots, we can visualize how the spread of them change across species, but we could add a little color to them just to make our graphs pop. Check this out. I'm going to add heat colors to that box plot, and here's what it does. Bam. These colors don't necessarily help you see it any better, in my opinion, but what I really wanted you to do was see how we can put colors on our graphs, because we're going to do it a little bit later when we do pairs plots. Now, a scatter plot helps us visualize data, and it's just sort of plotting your X versus Y, and we've done this before. Let's do it for petal length, and label our title, petal.length, and label our axis, our Y lab and our X lab, as species and petal length. Here's what we get for our first scatter plot. All right, again, you see that separation, but now we see the values. Previously, the box plot was giving us those summaries of those points, and now we get to see where all of those points lie. Okay. Notice on your x-axis, you've got species, so 0 to 50 is the first species, and then 50 to 100 is your second one, 100 to 150 is the third species. And then on your y-axis, you've got the petal length, and you can see how those are split up into three pretty somewhat distinct groups. What if we wanted to compare, say, petal width with sepal length and sepal width? Here you see those scatter plots side by side. Now look at petal length. Do you see some grouping in those? You can almost pick out the three different types. But sepal length, not so much, right? That data sort of blurs together. Looks like it's a lot harder for you to try to distinguish the three groups. So sepal length might not be a variable that we could use if we wanted to try to classify our data into different categories or different iris types. Here again, petal width and sepal width. Petal width seems to be doing a great job, right? It's like doing everything we need to try to separate these groups. But sepal width looks sort of like a blob that sort of goes down and then comes back up, and we're not really getting much information out of that graph. What might help if we could plot these variables against each other and maybe add some color to it so we can see exactly where the species are in these points. Now, if we've got a data set that just has a couple attributes, we can do a pairwise scatter plot, add color to it, and see what that looks like. Here, in the first row of this pairwise scatter plot, all the Y values are represented by sepal length, and that's on the Y-axis. And notice in the first column, all of the X-axis values are also represented by sepal length on the X-axis. Likewise, check out the second row. In the second row, all the Y values are represented by sepal width on the Y-axis. And in the second column, all the X-axis values are represented by sepal width on the X-axis. Now, it continues in this fashion for petal length and also for petal width. But I want you to bring your attention to the bottom left corner, the last plot in column 1. This plot has sepal length on the X-axis and petal width on the Y-axis. Now, since the upper and lower graphs are duplicates of each other, they're kind of giving us the same information. We don't really need one of them. But we can change our code so that instead, maybe we show the correlation between our variables. Let's do that and put it on the upper level. Now, remember, the correlation measures the strength of the relationship, the linear relationship between two variables. And it's going to range from -1 to 1, where values that are near 1 are going to give us a strong positive relationship. Values near -1 give us a strong negative relationship. And if we're near 0, that tells us that there's not really a relationship between the two variables. Here's a plot of our pairwise data. Notice that we've eliminated the upper plots and instead have put in those boxes the correlation between those random variables. Let me draw your attention to a couple of those. Notice the petal length and petal width have the highest correlation of 0.96. This is followed by petal length with sepal length, which has a second highest correlation of 0.87. Notice that the lowest correlation is between sepal length and sepal width. And that kind of came out in those plots, right? Because when we looked at the scatter plots, they were sort of a blob all over the place. Now, R has some built-in package called ggplot2 that's going to let you produce amazing figures. GG stands for Grammar of Graphics, and we use it to make quick, professional-looking pictures and graphs with very little code. Notice in this scatter plot of sepal length versus width, we've changed both the color and the character that we use to plot species. And it actually helps us to better distinguish between versicolor and virginica. Oh, but now this plot, check this out. Here's a plot of sepal length versus petal length. Now here we've used the same plotting character with different colors to separate the species. But notice, look closely, do you see the size of the dot? It actually varies according to a scale, which tells us the petal width. So each point on this plot gives us not 1, not 2, not 3, but 4 pieces of information. It tells us the sepal length, the petal width, and the species. Now we've seen histograms several times, and today we're going to do something slightly different. I want to focus on the bin size, and I want to show you how we can change the bins so that we look at different shapes of our histogram, because this is going to help us with visualization. Here's the code that we'd use to do that in R. Hist of, say, petal width, iris petal width, let's add 13 breaks in there. And so what that does, R is going to take that 13 and try as hard as possible to break our data set up into 13 bins. You see sort of there are 2 modes, center around 1.5, and then maybe a peak there at between 0 and 0.25. What if we change the size of that break, though? How's that going to change our histogram? Here, let's update our code. Let's try to get R to give us 25 breaks. Do you see how this spread the data out a little bit more, right? We don't really have that first hump like we did before around 1.5. Instead, we've sort of allowed that data to go slightly lower, but we've still got a peak at the beginning of the data set. In fact, we can customize our breakpoint by creating a sequence vector. Let's create a vector B, and that's going to range from the minimum of the petal width to the maximum of the petal width, and then I'm going to tell it how many breaks I want it to have. Here's a code that we could use to do that in R. We're going to set B equal to a sequence, and B is going to range from the minimum of petal width to the maximum of petal width. And now I'll set the length equal to just 11 and see what that histogram gives me. Okay, not too bad. Notice I put some color on that just to make it pop, but it's not really helping me see a whole lot of the shape of the distribution. One thing that we can use to get a better smooth version of a histogram is a density plot, and R does that with its density function. Here's a code if we wanted to calculate the density of petal width. We'd use the function density, iris petal.width, and plot that. Notice here, this is sort of like our histogram, but it looks sort of smoothed out. Right? We see those 2 humps along petal width, and we don't really see the jerkiness that we see in a histogram. Also, we could do this for every one of our variables. Here's the one for petal length and sepal width. Okay, now that looks funny. Almost sort of like a normal distribution. There's a peak there around 3, and then it sort of dies off and spreads to 2 to 4.5. Here's the sepal length density. That kind of goes up in peaks, almost sort of plateaus between 5 and 6.5 before it sort of comes back down. Now, these density plots are nice to look at when you're looking at the length and the width separately, but what if we wanted to say, look at them for all three classes all together? So now I want to think about the Setosa, the versicolor, and the virginica, and look at those corresponding density plots. Here's a plot of all three of those on the same graph. Notice how there's now separation between the first curve, which is tall and peaked, and the other two, which actually have some overlaps. So here you see the density plot of the petal lengths by the iris type. Now, we can take density plots and ramp them up one dimension to a contour plot, almost like put them in 3D on a 2D scale. So density estimation lets us look at higher dimensionals through the contour plot. A contour plot is just a graph that explores the relationship between three variables. You can think of this almost like a topological graph. If you were looking at a topological map where your X, Y, and your Z are the latitude and the longitude and the elevation, this is what you see in a contour plot. And we can do it on the iris data. Notice here in this contour plot, we've got elevated levels, which are the sort of centric circles that peak in the middle. And that tells us exactly where most of our points are clustered. On the x-axis, we've got petal length, and on the y-axis, we've got petal width. We could actually add a heat map to our contour plot, and this actually lets us see the colors along with their associated probabilities, and so those are the brighter colors. Look at this heat map. So same as the contour plot before, but now the higher shades of yellow are telling us where most of the density is. We're back to your favorite, the QQ plot. I don't know that we ever go a lecture without showing a quantile plot. But we can look at quantiles for this data set and compare them to a normal distribution by using the Shapiro-Wilk test. Because we want to see, does our data follow a normal distribution? Here's a QQ plot for virginica. Not too bad. Notice in the middle, those points sort of fall along the normal line pretty nicely. We've got a few outliers in there, but that looks pretty good to me. Versicolor, also, the first couple of points are really diverging from the line, but notice after that, it kind of gets its act together, gets toward normality. And Setosa, yeah, this is more like a step QQ plot in a way, much more segmented, but still follows closely along with the normal line. Now, just that visual examination isn't a strong enough statistical analysis for me to say that that's normally distributed. I mean, I could say it looks normal, you might say it doesn't look normal, and what are we left with? Fortunately, there's a test that we can do that formally tests for normality, and it's called the Shapiro-Wilk test. Now, typically for the Shapiro-Wilk test, if you have a p-value that's greater than 0.05, then you're good to go. Your data is normally distributed. So anytime you do this test, you want to look for high p-values. Let's do it on those three quantile plots that you saw. Here's a Shapiro test of quantile.setosa. And notice you have a p-value of 0.46. Great, we're safe. Let's check the other ones. Here's a quantile plot of versicolor. Again, nice high p-value, well above 0.05. We're good to go. And lastly, you see the quantile plot for virginica, which actually is the highest, 0.68. So this tells us that all three of our species, the underlying distribution is normal. And we've checked that not only by just looking at a QQ plot, but also formally through the Shapiro-Wilk test. Now, there are a couple of pitfalls that I don't want you to run into when you're looking at histograms. Because when you fluctuate that bin width, it can be good, but it can also be problematic. And here's an example. Let's do a histogram for our petal width. And let's say I want to only give it 3 bins, set my breaks equal to 3. Here's what that histogram looks like. Do you think that gives you any information about the shape of the data? Not so much, right? So this histogram has poor bin width. One solution is to overlay the density plot. So we learned how to do densities. The density is sort of like a smooth version of the histogram. This is really one way that we can tell if our histogram is accurately picking up the shape and the spread of our underlying data. Let's change our breaks again, this time 5. Notice how the histogram's trying to pull up some of that shape, But what happens when I overlay it with the density function? So here I can see that the density function in that second bin is showing that, hey, maybe there's some stuff there that's not quite coming up in my graph. What if we do one and just let R tell us what it wants to do? Just histogram of our data. Here's the image we get. And what happens when we overlay that with the density function? Very nice. So R's built-in bin sorting actually does a pretty decent job of giving you the appropriate number of histograms to accurately capture your data. Now, in this last example, we created a custom bin size because we wanted to sort of see a pitfall that we'd run into if we were trying to graph a histogram. And we can actually do this when we do other types of graphical analysis, just to check and make sure that what we're getting is accurate. But overall, graphical data analysis has actually become a major way to avoid many pitfalls in statistics. Now, once upon a time, graphical data analysis was time-consuming, hard to do, but all that's changed. In fact, I liked once upon a time because that was more consulting for me. But now I'm here to share the wealth with you. You should always take advantage of how easy it has become to display your data and to begin your analysis in your very own visual way.